thank you, and thanks for the invitation to speak, and yeah, thanks, Sandra. Fortunately, couldn't be here. Okay, so yeah, the HOD conjecture and its failure. Juan was telling me that this is a misleading title because it looks like I proved the failure of the HOD conjecture, and it also looks like I proved the HOD conjecture, and that would be a bad state of affairs. I didn't prove either. So it should have been called On the HOD Conjecture, and it's okay. So yeah, this is the first time I've ever given a talk whose title is propositionally false. I think maybe I've talked about false things before. Okay, so yeah, my introduction slide is very short. I just want to say what I'll be talking about. Mostly I'm giving, this whole talk is kind of an introduction to the series of 5 lectures I'll give next week, although they're called lectures 1 through 3, since I assume that I won't be able to finish one lecture, and no matter how much time I was given to finish it. So let's see. Yeah, so what is it about? Well, the main question is if the HOD conjecture is false, which seems like it will turn out to be, then what does V look like? And that sort of sounds like a philosophical question, like what should V be? But I really just mean what kind of universe of set theory is going to give us the failure of the HOD conjecture. Okay, so that's the theme. I don't know if I won't answer the main question, but I want you to keep the main question in mind. Sort of seems to me that the kind of universe that's going to give us the consistency of the failure of the HOD conjecture, really the HOD hypothesis. So the failure of the HOD conjecture is some kind of global generalization of determinacy. But yeah, I guess we don't know what that will look like, and there have been a couple proposals, or maybe really the same proposal by Grigor and Hugh this week about models where some global types of determinacy hold. So maybe that's it. So what is the HOD conjecture? Well, I have my pet formulation of the HOD conjecture. It was made by Wooden. This is an equivalent version of it. So it says if there is a supercompact cardinal, then you could prove in CFC, well, with the supercompact cardinal, that there's a definable well-ordering of the infinite sequences. So this is equivalent to the official formulation of the HOD conjecture. The problem is boldface definable. Yeah, definable from parameters. Definable from a parameter, a set parameter. Yeah, no. Otherwise, I would have refuted the HOD conjecture. Yeah, so it's important that it's boldface definability, and in order to confuse you, I put boldface in italics. Okay, so yeah, so the thing is, it is counterintuitive to say that there's a definable well order of ord to the omega. I mean, okay, we know that there, you can't prove from large cardinals that there's a definable without parameters well ordering even of the reals. Okay, but there is obviously a definable from parameters in ZFC well ordering of the reals, because well ordering can be your parameter, and then you can define it from itself. Okay, so that's kind of trivial, but to well order the reals, it seems like you need this parameter of size continuum. And then to well order the power set of the reals, you need an even bigger parameter, and then to well order ord to the omega from a parameter that's a set, seems like you would not be able to do that. So it's still counterintuitive, even in this boldface sense. Okay, so the conjecture was made by Wooden. I'll try to explain why it's a little bit more reasonable than it seems, but it's always been a counterintuitive conjecture. And let's see, it's at least 20 years old now. Do you know when the conjecture was first formulated to you? 20, okay, yeah. So something like it appears in the PMax book. Okay, and yeah, the conjecture is nice because it's connected to inner models for supercompactness, although it's not clear exactly what the connection is. Certainly a refutation of the HOD conjecture disproves a certain approach to building an inner model with a supercompact cardinal. Not so. Or another way to see it is, if this approach succeeds, and that's really the motivation for the HOD conjecture, then the HOD conjecture should be provable. Okay, and it's connected to determinacy, forcing. I'll try to keep the forcing people amused, and large cardinal axioms beyond the axiom of choice, Reinhardt cardinals. So yeah, the main theorem around the HOD conjecture is the HOD dichotomy theorem, which is also due to Wooden. This says if there's an extendable cardinal, then one of the following holds. Either a version of the covering lemma, Jensen's covering lemma, holds for HOD above kappa. So every set of ordinals of size, at least the extendable cardinal, is covered by an OD set, the same size. Or HOD looks really small. It can't compute successor cardinals correctly. In fact, every regular cardinal above the extendable is measurable in HOD. Okay, so you think there's a similar dichotomy for L. Right? Either L has covering, or every cardinal, infinite cardinal, is inaccessible in L. So this is some like way high up version of that for HOD. Okay. So the HOD conjecture is equivalent to the statement that one is actually provable. So the dichotomy theorem is not really a dichotomy at all. 2 is just impossible in the presence, not only of an extendable, but even a supercompact. But I think the spirit of the conjecture is just large cardinals. So if you could prove the HOD conjecture from whatever super duper huge cardinal, then we would all be very impressed. Okay, and yeah, how is this connected to the first slide? It's just if you have a cardinal kappa for which 1 holds, then you can get a definable from parameters well order of ord to the omega. You kind of just cover the set of size omega by a relatively small set, and then that's in HOD, and then you use as a parameter some well ordering of the power set of kappa. And then 2 implies that you cannot have such a well order. Okay, I just like this other way of formulating it because, well, it doesn't matter here, but you can describe it to a model theorist or someone who's forgotten what HOD is somehow. So it's completely elementary statement. Okay. Yeah, so why did Wooden conjecture 1? So this is related to inner models for supercompactness. The notion of a weak extender model, which Hugh mentioned very briefly during his talk. So an inner model is a weak extender model if kappa is supercompact. If basically, if it thinks that kappa is supercompact, and the measures witnessing the supercompactness of kappa come from measures witnessing that kappa is supercompact in V. That's all that this is saying. So formally, it's this statement, but just saying you take normal fine ultrafilters in V that witness the supercompactness of kappa, you restrict them down to N, and they still witness that kappa is supercompact. So theorem of Wooden, okay, so I combined two theorems and applied modus ponens so that it looks like these three people are involved. So if you have a weak extender model of kappa is supercompact, then every set of ordinals of size at least kappa is covered by a set in the model of the same size. So you have the covering theorem above kappa, the supercompact, not necessarily extendable for any weak extender model. So as Hugh mentioned, this is because weak extender models have the kappa approximation and cover properties. That's what Hugh proved. And then Hampkins and Reitz had shown that kappa approximation and cover imply the Jensen covering property. Okay, and then another property of weak extender models, also a property of models with a kappa approximation and cover. Yes, same size in V. Yeah, so it's the same as the covering lemma for L. Yeah, so it's not saying that N is correct about cardinals, which is what would be going on if you said it was cardinals in N. Okay, so weak extender models absorb all large cardinal properties, essentially all large cardinal properties above this kappa. So like if you have a huge cardinal above kappa, then it's still huge in the weak extender model. It doesn't happen right at kappa, and actually I have a slide about this, so showing that the HOD dichotomy theorem is optimal. You can't get away with less than an extendable in some sense. So this is kind of an apology as well. So Hugh showed that if you have an extendable cardinal, then kappa, then HOD is a weak extender model of kappa supercompact. That's how his proof of the HOD dichotomy theorem goes. Therefore, HOD has this covering property. Okay, and then the hope was that it would suffice to show in order to rule out 2, the second part, which of course can't hold at the same time as the first part. I say of course, but there's something you have to do there. The first part implies HOD correctly computes successors of singular cardinals, right? Just because covering implies weak covering. So you can't have that every regular cardinal is measurable if HOD is correctly computing a successor cardinal. Okay, so in order to rule out 2, it would suffice, in fact, to show that there's some weak extender model contained inside HOD. Okay, and that's the ultimate L hope. The plan for proving the HOD conjecture would be to build ultimate L and show as a weak extender model, and it's ordinal definable, it should be at least, and then it's contained in HOD, so HOD actually has to be pretty large, and then because of this dichotomy theorem, HOD has to be really large. It's itself a weak extender model. Okay, but in particular, this theorem implies that assuming the HOD conjecture, the least extendable cardinal is supercompact, right? Because HOD is a weak extender model for the supercompactness of kappa. And also the second extendable cardinal, the least extender, sorry, I think I said it wrong. The least extendable cardinal is supercompact in HOD. And the second extendable cardinal is extendable in HOD. And for some reason, I thought that, in fact, you could show that the least extendable cardinal was also extendable in HOD. And I even attributed this theorem to Hugh, even though Hugh never claimed such a thing because of his wisdom. And it turns out that it's just false. So this is a recent theorem of mine with Poveda. So, and I published this in a paper, so sorry, Hugh. I retract the claim that Hugh proved this. Because it's consistent actually that the HOD conjecture holds, really that 1 holds up here, the first bullet, and the least extendable cardinal is the least supercompact of HOD. So no supercompacts below stay supercompact. Okay, so this is, the tricky thing is it's pretty hard to force near it's just a forcing construction. Pretty hard to force near an extendable cardinal and preserve the extendable cardinal. You have to force all the way up to the extendable cardinal. This uses some technique of mine for forcing near extendable. Okay, so not really related to the main question of the talk because it's just a forcing construction. It doesn't really tell you anything about the HOD conjecture. Okay? And in fact, in another sense, you can prove the HOD dichotomy theorem from a weaker hypothesis. It just takes a little bit of reorganization of Hughes' proof. But what I showed is that if you have a strongly compact cardinal, which is significantly weaker than an extendable, right? It could be the least measurable cardinal. Then either HOD has weak covering above the strongly compact cardinal, or all sufficiently large regular cardinals, not necessarily all of them right above the strongly compact, which is what you get in the extendable case, are measurable in HOD. So either HOD is quite big, already at the level of a strongly compact, which could be the first measurable, so pretty low down, or HOD is really small, but you have to wait a while to find out. No. Yeah, I don't know how to prove in this context that HOD absorbs any large cardinal. So yeah, it's kind of an interesting question. Could you have a proper class of measurables in this context, but none of them measurable in HOD? I didn't think about it. Okay, and then there's... if you started with a model where V is equal to HOD. If you started, so that's a set forcing. So if you start with a model where the HOD hypothesis is, the HOD conjecture is false, HOD hypothesis is false, really, then you would get a model of where it's still false, right? It's preserved, the failure is preserved by set forcing. But if you start where it's true, so it does, these things are a little bit irrelevant to the actual question. Yeah, although it is open, it could be that you can just force the failure of the HOD conjecture from a supercompact. I mean, there's no, I mean, class force. You can't do anything by set forcing here, but it looks really hard, I guess. But there's no concrete evidence that it's impossible. Okay, so then there's a technical open question, which is related to Hughes' question, but more technical. So can you prove the covering theorem for HOD in this context? It's not, I only got weak covering. So it used to be that the statement of the HOD conjecture was in terms of weak covering, but Hugh improved this around 2019 to this full covering property. Okay, so I don't know if you can do that in this case, but it's a really kind of technical thing because I can cover every set of size lambda by a set of size like 2 to the 2 to the 2 to the lambda. So okay, so what's the connection with forcing that I mentioned? So there's this question of Magador's about whether you can singularize a cardinal by forcing while preserving a strongly compact cardinal. The point is that Perkry forcing creates a square, and in fact, whenever you singularize a cardinal to Coph omega while preserving its successor, you create a weak square, I'm sorry, and kill. So if you do it above a strongly compact, it's dead. So let's see. I say it's a long-standing question. I think it is, but I couldn't find any reference for it. It seems to be a folklore question. Has anyone seen this written down? Anyway, so I didn't answer this question, but it is related to these kinds of things. So suppose you have a weakly homogeneous forcing extension of V. Then you can prove that you didn't singularize any regular cardinals above your strongly compact. So if you preserve a strongly compact by weakly homogeneous forcing, you must have you must be preserving, well, you can't singularize a regular cardinal without collapsing it. That's what this is saying. So one thing about this is it doesn't actually I'm not assuming the HOD conjecture. It's just that the proof of the HOD conjecture gives you this kind of thing, above a strongly compact. It doesn't even really need weakly homogeneous so much. Just needs see the omega club filter inside of the ground. Okay, so yeah, this is what I'm going to talk about in my first lecture. So I'll give what I think is the shortest possible proof of the HOD dichotomy theorem, and both the strongly compact one and the extendable one that can sort of be unified. And I'll talk about the generalizations that give this kind of theorem on forcing. So yeah, there's questions about what forcing can do in the presence of large cardinals, and that's one way to think about the HOD conjecture if you're trying to refute it by a forcing construction. And this sort of rules out a tiny bit. Because it's hard to control HOD if you're not weakly homogeneous, so how are you supposed to, well, anyway. To me, what's interesting is, yeah, we know that the failure of, that you can't force the failure of the HOD conjecture by a set forcing, but the HOD conjecture is really a global thing, so it seems sort of clear that you wouldn't do it by a set forcing. So what can you prove more locally? Anyway, that's all for the first lecture. How much time do I have? A little less, given your slow subtraction. Okay. Okay, so yeah, now I want to talk about some things that make the failure of the HOD conjecture look like it's related to global determinacy principles. And these are omega strongly measurable cardinals. So the HOD conjecture states that either V is close to HOD or else every regular cardinal is measurable in HOD. But in fact, in the second case, the measurability is witnessed in a very strong and surprising way that looks a bit like what you see under the axiom of determinacy. Well, okay, so I would just want to define what an omega strongly measurable cardinal in HOD is, and let me do it in this sort of non-standard way. So say an OD stationary set is eta unsplittable if you can't partition it in an ordinal definable way into eta disjoint stationary sets. So all the sets in the partition have to be themselves ODs if it's an ordinal definable partition, but I want the whole partition to be OD. Okay. So Wooden showed that a regular cardinal is, if it has an eta unsplittable OD stationary subset, and the eta is small relative to delta, then delta is measurable in HOD. I mean, so it's clear. The point is, if it has a 2 unsplittable stationary subset, then that set is an atom of the club filter restricted to HOD. So the club filter restricted to that stationary set gives you a measure, a delta complete normal ultrafilter on delta in HOD. But eta unsplittable, it's not so obvious, but there's this Ulam splitting argument that shows that if you have an eta unsplittable set, then there's contained in it, there's a 2 unsplittable set. So that's how this proposition works. And then a cardinal is omega strongly measurable in HOD if the coph omega points are eta unsplittable for some eta much less than the cardinal, so with 2 to the eta of HOD less than delta. So omega strongly measurable cardinals are measurable in HOD, and in fact you can partition the coph omega points into fewer than eta many pieces, and each piece is a 2 unsplittable, or an atomic stationary set with respect to HOD. So it looks, well, I'll give you some examples of omega strongly measurable cardinals in a second, but it looks like things you get from AD. So in all of the HOD dichotomies, every time I said measurable, I could strengthen it to omega strongly measurable. Yes, that is what that quantifier meant. For some reason, I was obsessed with fitting it on one line, but yeah, you're right, it became ambiguous. Yeah, there is some eta such that this thing happens. That's what it means everywhere. I'm sorry. Yeah, not for all etas. Okay, so what most natural situations where you get omega strongly measurable cardinals are situations where the axiom of choice is false. So, for example, if you have an infinitary partition property, then at delta, then delta is omega strongly measurable. Really, the omega club filter on delta is an ultra filter. Okay, so it's also, so it's every stationary, like the Kof omega points are they're unsplittable, absolutely. Okay, under AD plus, you get this at actually every regular cardinal below theta, not the partition property, I don't think that's known, but the omega strong measurability. And when I say omega strongly measurable here, I mean, okay, I could mean omega strongly measurable in HOD, but it's the stronger thing. It's like omega strongly measurable in V. You can't split the sets at all. If I0 holds, then in L of V lambda plus 1, every regular cardinal between lambda and theta is omega strongly measurable. Oh, theta, sorry, it's the theta of V lambda plus 1. So it's the least ordinal that you can't surject V lambda plus 1 onto, it's bigger than 0. Okay, so yeah. So yeah, I'll talk more about I0 later, but it's a really strong hypothesis, large cardinal hypothesis that gives you structure in this model, L of V lambda plus 1, which is analogous to the structure of L of R. So this is just one instance of that analogy. And then Wooden showed that if there is a Reinhardt cardinal, then all sufficiently large regular cardinals are omega strongly measurable. Although in this case, you can't get as much mileage out of this. Let's see. You can't get as much mileage out of it as you might want because it's not obvious, although I did show it later, that the club filter on these regular cardinals is complete enough to run this Ulam splitting argument. So it's not obvious how to get from here to showing that all the sufficiently large regular cardinals are measurable in HOD, but it's actually true. Not quite, but a lot of them are. Okay, the omega club filter, you can get an ultra filter. Anyway, okay, so there are these two situations where we get omega strongly measurable cardinals from AD. I guess I'm counting the partition properties as something like AD, and from these choiceless large cardinals, and I guess I'm counting I0 as something close to a choiceless large cardinal, even though it's usually considered in the context of choice. Remember, Reinhardt cardinal is a J from V to V. Hugh talked about super Reinhardt cardinals, which are a little more complicated, but all of these things are inconsistent with the axiom of choice. L of V lambda plus 1 is a model that satisfies the negation of the axiom of choice. So all these natural instances of omega strongly measurable cardinals appear in the context where choice is false. Okay, so yes. Yeah. Yeah, you have to go high up. At least, actually, it's above the lambda of the Reinhardt cardinal where you get this omega strong measurability. Oh yeah, another thing is, I say all sufficiently large regular cardinals, but it wasn't known when Wooden showed this that there were any regular, that the regular that there's a proper class of regular cardinals. So I guess with large cardinals above, but there actually has to be a proper class. Okay, so Emax forcing over L of R can give you a model of ZFC. where there are some omega strongly measurable cardinals. I mean, it's a homogeneous forcing, so the things that were omega strongly measurable in HOD are still omega strongly measurable in HOD. And there are more trivial things you could do, like just well order the reals, and you get one. Omega 1 is still going to be omega strongly measurable in HOD, and these other things aren't going to be cardinals. Omega 2 won't be a cardinal. Okay. So many author paper used Pmax forcing again over a larger model of determinacy to get 3 regular cardinals to be omega strongly measurable in HOD, and notably one of them is the theta of this model. Okay, so that's a kind of interesting property to have. So I think these models are, I say chain type models. I think they're somewhat similar to the models Gregor was talking about. Okay, and then pretty surprisingly, Ben Nuria and Hayut showed from pretty weak large cardinal hypothesis that you can have all successors of regular cardinals omega strongly measurable in HOD. But it's not known how to get this at a successor of singular from anything weak. I mean, they almost got an omega strongly measurable cardinal in HOD from at a successor of singular countable cofinality, but they didn't quite get there. Okay, assuming I0, you can generically well order V lambda plus 1, so it's sort of analogous to the first, the Pmax forcing, except I'm just forcing GCH at lambda to get a ZFC model where a successor of a singular strong limit cardinal is omega strongly measurable. So you're forcing over L of V lambda plus 1 itself to get choice. And you had some way of, sorry, Hugh, you had some way of doing this and the first one together to get? Mm-hmm. Uh-huh. Yeah. Mm-hmm. Oh, that's really interesting. Coph omega. Uh-huh. Okay. Okay, so the failure of the HOD conjecture, so how do you get models where the HOD conjecture is false? Wooden showed that by forcing choice over a model with choiceless cardinals, although I'm not sure exactly about the status of this. This is what it says in SEM 1, but you were using Vopenka cardinals the other day. Yeah, you have to state supercompact the right way. So you can force choice and preserve the supercompacts. And then in the final model, it's a homogeneous forcing extension. So HOD is still just as small as it was when you had the Reinhardt cardinal. And therefore, the HOD conjecture is false in that model. Sort of the HOD conjecture is stated about numbers. Okay, so if Reinhardt cardinals are consistent, then the HOD conjecture is false. I mean, Reinhardt cardinals plus enough supercompact cardinals, and the HOD conjecture is false. Or, you can look at it as if the HOD conjecture is true and the ultimate L conjecture is provable, then Reinhardt cardinals are inconsistent. So take it whichever way you like. Yes, yeah. Maintaining the choice large cardinals. But yeah, you can force preserving huge cardinals and it's just anything you can do with a master condition argument. It's the forcing Hugh was talking about. So it preserves pretty much all large cardinals. Yes, but only ones that are compatible with choice. So it's sort of a nice picture for, I don't think I have a lot of time left, do I? 10 minutes? Okay. All right, so let me talk more about the I0 axiom. So I0 says that there's an elementary embedding from L of V lambda plus 1 to L of V lambda plus 1, critical point below lambda. So the analogy is supposed to be between L of R, which is L of V omega plus 1, and L of V lambda plus 1. The axiom of determinacy for L of R, and this axiom I0 for L of V lambda plus 1. So that's the, I think, original motivation for formulating this thing, as well as the natural attempt to strengthen rank-to-rank embeddings. So things like there's an embedding from V lambda to V lambda, which are the, the last axioms compatible with the axiom of choice before you get to the Kunin inconsistency. So you can generalize the structure theory of L of R to L of V lambda plus 1 by completely different proofs, mostly due to Wooden, also due to some of this is due to Scott Kramer and others. Okay, sorry if I'm forgetting you, she, and sorry. Okay, so let's see. So certain questions about L of V lambda plus 1 are also sensitive to the structure of V lambda. So by forcing over V lambda, you can change its structural properties, and this turns out to change the global, or like between lambda and theta properties of L of V lambda plus 1, the places where you would expect an analogy between, to have the analogy with L of R. So you can force down low, and then I0 is preserved, and now you have sort of different structure theory above. So on the one hand, this means that there are questions about L of V lambda plus 1 that you can't answer from I0, so that breaks the analogy with L of R and determinacy a little bit. On the other hand, it means that so you can guess based on L of R what you should want the structure of L of V lambda plus 1 to be. And that's now going to give you information about what V lambda should look like. V lambda, maybe model of choice. So one of these things Hugh defined called the ultrafilter axiom, not to be confused with the ultra-power axiom. That's my fault. So this says that for all gamma less than lambda, the gamma club filter on lambda plus is an ultrafilter in L of V lambda plus 1. Okay, so this is not provable from I0. So it's almost provable actually that the omega club filter on lambda plus is an ultrafilter, but for omega 1, it's known to be independent. It could be provable for omega. So the question is, and all you have to do is force below V lambda. So the question is, what is the right theory for V lambda that might get you this? It seems very hard to force this to be true. So yeah, so does this decide anything about the structure of V lambda? Hugh has posed the question of whether this decides CH, and it's still open. It could be that this structural principle, in analogy to L of R, where this kind of thing happens, is actually just implies CH, or refutes CH. Neither one is known. Okay, another question you could ask is this one under Martin's maximum. Not whether Martin's maximum implies this, because it can't, but you could ask whether it refutes it. Okay, one thing that does imply this, which is maybe a little ridiculous, but I still want to think about it, is the statement that lambda plus is a strong partition cardinal. This is kind of where these things come from. Or even a weak partition property would be enough. So the problem with that as a principle for L of v lambda plus 1 is as soon as gamma hits omega 1, you've refuted the axiom of choice in v lambda. You kind of want to, because you can prove some forms of determinacy, Suslin determinacy, or omega 1 Suslin determinacy from partition properties. So we want to consider L of v lambda plus 1 in the context of AC, but this natural generalization of property in L of R actually refutes AC down low. Okay, so it may be reasonable to try to study L of v lambda plus 1 in a context where AC fails in v lambda. These models that Hugh is looking at seem to give a candidate for a place you might find such a model. Okay, so I just want to talk about what happens if you assume this. So assume I0 holds at lambda, and you have this partition property. So this is in the context of ZF. Then the HOD conjecture is false. Okay, so I need DC. I have 4 minutes. Yeah, I'm not going to finish. Oh, I guess I could. 3 minutes, 3 slides. One of them says thanks. I could skip that one. No. Okay, so the way this actually uses, it's easy given all these techniques, but it uses a lot. So you have to force choice, obviously, down below v lambda, which you can do by Hugh's technique for forcing choice, because you have lots of large cardinal axioms in v lambda. You use the partition property to get the determinacy of certain ordinal games. I'm actually using the perfect set game, Moskovakis' perfect set game on ordinals. So you get some ordinal determinacy from these things. And you use inverse limit reflection to sort of pump up the completeness of the partition measures. So to get away with just DC, that's why I need DC. Well, I need DC a couple times. Okay, so yeah, there's something interesting there, and it's using I0 at the same time, sort of, as the partition property. So maybe this is consistent. And Hugh showed me an argument on Wednesday. I'm pretty sure it implies that this theory gives omega 1 is measurable. Well, and every countably complete filter on an ordinal extends to a countably complete ultrafilter. And the partition property at lambda implies there's a definable well ordering of all the countably complete ultrafilters on ordinals in v lambda. So that's a lot of structure below lambda. I mean, whether it's consistent, it's unclear. It's a lot of structure. So if it is consistent, then it's a really interesting model. Well, it's not a model, it's a theory. Yeah. Well, a HOD conjecture technically is whether you can prove this statement. So it's just false, right? I get a model where the HOD hypothesis fails. But I didn't want to make the distinction. There's a good reason to make the distinction. Okay. Okay, the last thing I'll talk about is what kind of large cardinals you get in HOD from the failure of the HOD conjecture. So you can get some high Mitchell order measurable cardinals just from the omega strong measurability, but it embarrasses me that I couldn't figure this out. Does HOD necessarily contain a measurable cardinal kappa of Mitchell order kappa? That is not really clear. And okay, so what I'll do is show this thing, which has a kind of crazy hypothesis. So if kappa's strongly compact and you have an omega strongly measurable cardinal in HOD above it, so it has to be a regular cardinal, cofinality of its successor is uncountable, then HOD thinks that delta is delta plus supercompact. So, and you can do the same thing if delta plus omega plus 1 has uncountable cofinality, then delta is going to be delta plus omega plus 1 supercompact in HOD, sort of, etc. I mean, obviously has to basically be an accessible cardinal, not weakly inaccessible cardinal above delta. Okay, and it involves this ZFC result on weak covering from HOD, which I proved with my graduate student, David Casey. So this tells you all the possibilities for cofinalities of successors of regulars in HOD. There are exactly 4. They can all occur distinctly. Okay, and I guess the delta plus omega plus one needs a generalization to successors of singulars, which is a little harder to state. Yeah, that's a ZFC theorem. Okay, thanks.